Dear student, today I am going to continue the next part of strength of organic acids and bases. In previous video, we have already started the discussion of aromatic bases. So in that first factor we discussed, that is the introduction of electron donating group in previous video. Now in this video, I'm talking about the introduction of electron withdrawing groups on aromatic bases. So this is the first example: aniline, metanitroaniline, paranitroaniline, orthonitroaniline. Look at the pK values. pK values goes on decreasing. As the pK value goes on decreasing, so basicity and pK value, they are directly proportional. pK decreases, basicity also decreases. So from A to D, basicity goes on decreasing. Now, why the basicity goes on decreasing? There is a presence of nitro group, and as you know, nitro group is electron withdrawing group. So how it shows the electron withdrawing effect? Look at the resonance effect here. Nitrogen electron pair of NH2 group get delocalized like this towards the oxygen atom of nitro group. Because of that, due to this resonance, now nitrogen, there is a positive charge. Positive charge means no electron density with this nitrogen. So because of that, as the electron density is not available on this nitrogen atom, then it won't donate its electron density to a proton, and hence the basicity decreases. So in case of paranitroaniline and orthonitroaniline, we can see such type of resonance effect. But if the NO2 group is placed at meta position, then NO2 group not involved in resonance, rather than it shows electron withdrawing inductive effect. Because of that, as we know, the always minus R effect is more powerful as compared to minus I effect. Hence, the basicity of metanitroalanine is more basic, or it is a strong basic base as compared to paranitroaniline and orthonitroaniline. So you can see the resonating structure of paranitroaniline. Now let us discuss the metanitroaniline. Look at here, in metanitroaniline, the NO2 group not involved in resonance. Only the pH double bond, that is the double bond of phenyl ring involved in resonance, so that electron pair which are present on this nitrogen atom get involved in delocalization due to only the phenyl ring. So as compared to the previous resonance effect, this resonance effect is less powerful. The reason here is carbon carry the negative charge here, while in previous structure, oxygen bears a negative charge. As we know, carbon is less electronegative than oxygen, therefore this resonance effect is less powerful. But as we compared with aniline, this type of resonance is possible, but at the same time, this NO2 group shows electron withdrawing inductive effect. Because of that, it is less basic as compared to aniline. Now look at here, in case of orthonitroaniline, now nitro group involved in resonance, and you'll get this type of structure. So NH2, as it donates its electron density, so therefore there is a positive charge on this nitrogen. Oxygen accept electron density, so negative charge is on oxygen. So there is a good coordination between the positive charge of nitrogen and the negative charge of oxygen. Such type of coordination is possible in case of orthonitroaniline, while such type of coordination is absent in case of paranitroaniline. So because of that, this resonance is more powerful as compared to paranitroaniline. The same, whatever I explain now, the same is written over here. The pK goes on decreasing from A to D, so basicity also decreases from A to D. In compound A, there is no nitro group, so electron withdrawing inductive effect is absent. Electron withdrawing inductive effect decreases electron density on nitrogen atoms, so the compound B, C, D availability of electron density is less as compared to compound A. Hence, compound A is a strong base among all. When an electron donating group is present at ortho and para position, then it shows a prominent effect. In compound C and D, NO2 group shows electron withdrawing resonance effect, so it decreases electron density on NH2 group. So the availability of electron density is less for donation to a proton as compared to compound B. Only -I effect shown by NO2 group is present in case of metanitroaniline, that is compound B. Hence, compound B is strong base as compared to C and D. Again, the resonance effect shown by the ortho NO2 group is more effective as compared to para-nitro group because there is a good coordination between NH2 group and nitro group as shown in figure. Hence, in compound D, the -R effect is more powerful as compared to compound A, B, C. So, compound D is weak basic than compound C. In compound B, electron withdrawing inductive effect shown by nitro group is less powerful as compared to -R effect. So, compound B is strong base as compared to C and D, but weak as compared to A. Now, the next point is heterocyclic bases. So what is the meaning of heterocyclic? Heterocyclic means a heteroatom is a part of a ring compound. So now nitrogen is in a ring. Therefore, we call it is a heterocyclic compound. So this is an example of a pyridine where pK value is 5.21. This one is the aliphatic amine. So that is triethylamine, where the pK value is 10.75. So you can see the drastic difference here is 5.21 and 10.75. That is, triethylamine is more basic as compared to pyridine. So what is the reason behind it? In pyridine, the nitrogen atom is sp2 hybridized, while here this nitrogen atom is sp3. Now what happens because of the sp2 carbon, the lone pair of electron present on nitrogen atom not involved in resonance. Again, one more feature is that these electron pairs not involved in resonance. The reason is the, what is the Huckel rule? Huckel rule states that there has to be a presence of 4n plus 2 pi electron, that is, as the n stands for number of ring. So here only one ring is present. So how many total electrons are there? 6 pi electrons, and 6 pi electrons are already there in the ring. So electron pair, lone pair of electron of this nitrogen atom is not a part of a aromatic ring. So because of that, these electron pairs are readily available for donation. But the thing is what? As it is a sp2 hybridized sp2 hybridized nitrogen atom, due to this, the percentage of S character is more. In sp2, the percentage of S character is 33.33%. Because of that, the electrons are more tightly held by the nucleus of the atom, and that nucleus is the nitrogen nucleus of the atom. So because of this, it is very difficult that this electron pairs not readily get donated. So this weakness is found to be characteristic of bases in which nitrogen atom is multiply bonded. Due to that, its lone pair of electrons is accommodated in an orbital that has more S character. The electron pair is drawn more closer to the nitrogen nucleus and held more tightly by it, becoming less available for donation. So as these electron pairs not involved in resonance, so we can say that these electron pairs readily available for donation. But the one more feature that this nitrogen atom is sp2 hybridized atom. Because of this electron pair is strongly held by the nucleus. Hence, it's not possible that ready donation. Because of that, pK value get decreased as compared to triethylamine. Now, this is the next example. So triethylamine, pyridine and acetonitrile. Look at the pK value 10.75, 5.21 and minus 4.3. So you can see here this nitrogen is sp3 hybridized, this nitrogen is sp2 hybridized, and now this hydrogen is sp hybridized. So going from A to B to C, the unshared pair of electrons are in sp3, sp2 and sp orbitals respectively. So S character goes on increasing in the same order. So as the S character increases, the electron pair is drawn more closer to the nitrogen nucleus and held more tightly by it, becoming less available for donation. Hence, the basicity goes on decreasing in the same order, that is A to C. In fact, acetonitrile is the weakest base among all. So, as the unsaturation increases or the sp3 changes to sp2 changes to sp, the basicity of amines go on decreasing. Now this is the next example. This is a triethylamine and this one is quinacridine. This is again, look at the basis, that is pK value 10.95 and this is 10.75. This quinacridine is little bit a strong base as compared to triethylamine. The reason behind is this compound is a bridge bicyclic compound. So in this compound, that this nitrogen atom and substituents which are present now, this is first substituent, this is second substituent, and this one is third substituent. That is again this nitrogen is a tertiary nitrogen. Same, this nitrogen is also tertiary nitrogen. But as it is a bridge compound, the system is tight. There is no flexibility for this substituent, for this substituent, and for this substituent. Because of there is no flexibility, there we call this system is tighten up, and hence this electron pair readily available for donation. And one more thing, all these alkyl group shows electron donating inductive effect. So this transfer its electron density to nitrogen atom, and hence we can say there is a presence of in tertiary amine, the plus I effect is more. Because of this, the plus I effect, the electron density is more on this nitrogen atom. Same here, the electron density is more on this nitrogen atom. But only thing is what, in case of triethylamine, as the system is not tight enough, so there these three ethyl groups little bit causing a steric hindrance for these electron pairs for donation. Hence, as compared to this quinacridine is strong basic 10.95. Now this is the next example. In this example, so pyrrole, this is a pyrrole molecule. In what side, as pyrrole, if we consider it is a base, then pyrrole has to abstract the proton. If we consider this act as an acid, then base has to abstract its proton. Let us find out what is the role of pyrrole. Now the pK value of pyrrole is minus 0.27, indicate it is very weak base. Now this electron pair of this nitrogen electron pair, pyrrole is an aromatic compound. So this electron pairs involved in resonance. These two electrons and these two electrons. So these 6 pi electrons are the part of our aromatic system. As it is a part of aromatic system, therefore this electron pair involved in resonance. So you can see this involved in resonance, hence what we can say that electron pair not readily available for donation. So like that, this involved in the resonance. So because of that, now this carbon abstract the proton. So instead of nitrogen directly donate its electron density to this proton and abstract the proton, that is not possible. This carbon abstract the proton because there is a maximum electron density on this carbon due to this type of a resonance rather on the nitrogen atom. Because of this, the nitrogen never donates its electron density to a proton. Rather than that, the protonation takes place at alpha carbon atom. Because of this, as nitrogen not donate directly its electron density to a proton, therefore it is not a base, or we can call it is a very weak base. On other hand, if we consider that whether the pyrrole acts as a acid or not, then we are going to treat it with a base, sodamide, NaNH2. Now what NaNH2 will do, NaNH2 take out this electron density, NaNH2, that is NH2 minus, take out this proton and get the negative charge on this nitrogen atom. So because of this structure, now this electron pairs involved in resonance. So because of this resonance, this anion is stabilized due to resonance. So instead of a base, now the pyrrole can also act as a weak base. The reason behind it, the proton which is attached to the nitrogen atom showing a acidic character, and due to the whatever the conjugate base result after the donation of proton, that conjugate base is stabilized by way of a resonance effect. So that can act as a weak acid also. So pyrrole, it is a weak base, at the same time it can act as a weak acid. Now this is the next example, pyrolidine. In case of pyrolidine, that is the saturated analog of pyrrole, and this is diethylamine. Both the amines are secondary amines. So ethyl group, and here it is the ring bond, donate its electron density to nitrogen atom. So both bonds are showing the electron donating inductive effect. Same here, that ethyl group showing its electron donating inductive effect. Look at the value, pK value 11.27 and 11.04. So little bit basicity of pyrrolidine is more as compared to the diethylamine. The reason is the lone pair of electrons are readily available for donation due to the plus I effect, and hence the nitrogen atom donate its electron pair to a proton, and hence both these compounds act as a base. Now the next point, specific and general acid-base catalysis. Now the first point, specific acid catalysis. What is the meaning of this? If you carry out the reaction, then some reactions are catalyzed only because of certain acid, and that type of reactions we call it is a specific acid catalysis reaction. So here it is the acid catalyzed reaction in which the rate of reaction is found to be directly proportional to the H plus ion, that is protonated water, concentration in aqueous media. So this reaction is only catalyzed by H plus ion. In this type of reaction, the rate of reaction increases as the pH falls. So more the concentration of H plus ion, then the rate of the reaction has to be fast. This is known as a specific acid catalysis reaction because H3O plus is the only species that catalyzes the reaction. The reaction rate is found to be unaffected by the addition of other potential proton donors such as NH4 plus. If we add other proton donor, then the rate is unaffected by this proton donor. So this is called as a specific acid catalysis reaction. The rate is dependent on only the protonated water, that is the H plus ions present in a aqueous medium. In this reaction, there is a rapid reversible protonation of the substrate before the slow red determining state. So let us see what is the example and the mechanism of this reaction. So example is hydrolysis of acetals. Here the rate of reaction depends on the protonated water as well as the reactant. The reactant is acetal. So this is the mechanism of reaction. Now this is an acetal. It reacts with the protonated water. So oxygen electron pair accept the proton of a protonated water so that the positive charge on this oxygen get neutralized, and this is very fast process. And after abstraction of this proton from the solvent, then the electron pair which are present on the other ethoxy group that forms a double bond here, and because of that this group is departed. Now this step is a slow step. So look at here, why this is a slow step. Say this oxygen carrying a plus, oxygen is carrying a plus charge over here. So there is removal of one ethanol molecule, and this is CH3, C double bond O, and this O is attached to ethyl group. So there is a positive charge of oxygen because the valency of this oxygen is 3. That is 1, 2 and 3. 3 valency, that's why it is a, there has to be a positive charge. Now what is the next one? That is proton, that is again the solvent which attack on this carbon, so that this bond is going to break and it neutralizes the charge on oxygen atom, and it gives what? So after donation of electron density of oxygen of water molecule, electron, once it donates its electron density, then oxygen having a positive charge here. Now in the next step, that this oxygen electron density accept the proton from this and neutralize the charge on this oxygen, so that it gives a positive charge on this oxygen, and at the end there is a departure of ethanol again. So it gives what? CH3, C double bond OH. So it forms a double bond here and depart this group. So it gives what? Acetaldehyde plus ethanol. So this reaction is catalyzed by only the that is a protonated water or H plus ion concentration in aqueous media. Now the first protonation is very fast, while the next steps are slow. Now the second point is general acid catalysis reaction. Now in previous one, that is specific acid catalysis reaction, the reaction is influenced by only one type of acid group, that is H plus in aqueous media. But here these reactions are catalyzed not only by H plus in aqueous media but other acids in the system. This reaction becomes important at higher pH. Example, pH is nearly about 7. This is known as general acid catalysis reaction because catalysis by proton donors and not by H3O plus alone. So here the proton donor, other proton donor also influence the rate of reaction. In this reaction, there is slow protonation of the substrate, red determining step, and is followed by a rapid conversion of the intermediate into product in more than one step. Example, hydrolysis of orthoesters by other acids HA. The other acid is HA. Now the rate of reaction is equal to, that is the rate of reaction when it is considered with the protonated water, that is the protonated water into the concentration of the reactant, that is the orthoesters, while the another catalyzed acid, that is HA, so plus the rate constant, that is product of concentration of HA into product of concentration of reactant. So this is in that way, the rate of reaction depends upon the rate because of the H3O plus and the rate caused by HA. Now look at the mechanism. This is the orthoester. So again, the electron density or the unshared pair of electrons of oxygen forms a double bond here, so that this group going to break and it abstract the proton from HA and depart the A as A minus. Now this is a slow step. After this, once the electron density of this oxygen donated, so there is a positive charge on this oxygen, and now one ethoxy group is eliminated, that is ethanol and A plus, plus A minus. Now there is a resonance with this. This electron density forms a double bond here and neutralize the charge on this oxygen. So it remains in a resonance, therefore it is a stable one. In the next step, the water molecule attack on this and neutralize the charge on oxygen. Now this is a fast step. So due to this, again in the next step, oxygen of ethoxy group extract the proton and neutralize the charge on oxygen of the water molecule, and then at the end there is a formation of a double bond over here and it depart the ethanol molecule. So it gives CH3, C double bond O, that is ethyl acetate plus ethanol. Now the third point is specific base catalysis. Specific base catalysis, like in a specific acid catalysis, the reaction is influenced by H plus ions from aqueous media. Now here specific base catalysis, the reaction is influenced by OH minus concentration in aqueous media. In this type of reaction, the rate of reaction increases as the pH increases. So as the OH minus means the rate of reaction is fast at higher pH. In this reaction, there is a rapid reversible proton removal from the substrate before the slow rate determining step. Example of this reaction is base catalyzed reversal of aldol condensation, in which the rate of reaction depends upon the concentration of OH minus ions and concentration of reactant. The mechanism for the reversal of aldol condensation is believed to proceed as follows. Now this is a bit, aldol condensation means the product of aldol reaction is beta hydroxy carbonyl compound. So this is a alpha carbon next to the carbonyl carbon. This is a alpha carbon and this one is the beta carbon. So in this case, the hydroxy group, as it is a base catalyzed reaction, therefore hydroxy group abstract the proton from this is a base abstract the proton of this beta hydroxy group. So due to that, there is a generation of one minus charge on this oxygen, and this oxygen now undergo redistribution of electron density. So this O minus forms a double bond here, so that this carbon-carbon bond is going to break, and that step is a slow step. So due to this, it gives acetone plus CH2 double bond O minus and CH3. That is, what is the aldol reaction? Aldol reaction, now this is a self-aldol condensation reaction, that acetone molecule in presence of NaOH, it gives beta hydroxy carbonyl compound. So that is the reverse. This is the reverse reaction of aldol condensation reaction. So in reverse reaction, again the hydroxy group abstract the proton of a beta hydroxy group and the reaction get reversed. Now this is the last point, general base catalysis. Now general base catalysis reaction, bases other than hydroxy group are involved. In this reaction, there is a slow removal of proton from the substrate, rate determining step, and is followed by rapid conversion of intermediate into product is more than one step. Base catalyzed bromination of acetone in an acetate buffer. So here again the rate of reaction depends upon the concentration of hydroxy and the concentration of reactant as well as the concentration of acetate buffer, that is MECO minus into concentration of reactor. So the addition of this two product, that is the rate of reaction. Now, how is this reaction? The reaction is believed to proceed as follows. So B is hydroxy minus or acetate. Now this is the acetone and the alpha proton is abstracted by the base. So base abstract this alpha proton, and because of that there is generation of a carbanion on this alpha carbon. In the next step, this O minus forms a double bond here, and this alpha carbon attack on bromine and depart the Br minus. So this is a fast step. So overall, this is what alpha halogenation at the alpha halogenation of acetone plus Br minus. So this reaction is catalyzed by acetate ion, as well as this reaction can be catalyzed by hydroxide also. So if the reaction is catalyzed by more than, that is not only the rate of reaction not only depends on hydroxide, but the rate of reaction depends on other bases, then this is called as a general base catalyzed reaction. So for this you refer the Brooks.